The title of this talk is Python for Operational Research in Healthcare. So you're all here, so I'm guessing you all think Python's awesome. And we're always hearing in the news that there's some crisis in the healthcare system. So any work done towards that must be worthwhile. But what's this operational research thing? So this is my slide to try and describe what I think of operational research. So operational research, or OR, as I'll call it from now on, a lot of mathematical techniques involve data analysis and statistics. It also involves other mathematics, which we use for optimization and modelling, for example, linear algebra, combinatorics, probability theory, and calculus. And the kind of problems that we'll be solving in operational research, I'll go through with the examples of this talk. So operational research is said to have started in around World War II for military applications. And a story that's often said, which I like to say, is that the first problem that was solved by operational research was that fighter planes were really visible from U-boats against the night sky. And they got a lot of mathematicians together and they come up with what I think is a really elegant solution. They just painted the underbellies of the planes white because they were not visible against the night sky. And I like to say this because it shows that big problems can have elegant solutions which might not actually use that much mathematics. So I'm a PhD student doing operational research as my thesis, and we often get taught on operational research courses that you need specialist software, often expensive specialist software, to be able to do this sort of work. But I don't believe that. I think Python's extensive collection of high-quality libraries does the job for you. So I'm doing my thesis in this area, and sometimes, just like this cartoon, I feel like it's a bit cheating. I just import my thesis, and someone else has already done all the work for me. So in this talk, I'll show which libraries that I use to solve some of these sort of problems. Said that data analysis and statistics is a lot of what we do, and that sort of underpins everything, I feel. As a foundation for all my work, the libraries I use is pandas for data structures, matplotlib for visualization, and numpy and scipy for all the numerical stuff. Through statistics in Python, scipy has numerous hypothesis testing functions. As an extension of this, scikit-learn has a number of machine learning algorithms. Here using a clustering algorithm, we can cluster some patients based on body shape. But Python's really renowned for this sort of thing, so I'm not going to go over that. I want to look at some more traditional operational research problems. So here's a problem, it's a scheduling problem, a nurse rostering problem. So we have a ward where at each hour of the day, we have a different minimum number of nurses required to be on duty. So between 9 and 10, we need at least 7 nurses on duty. Between 10 and 11, we need at least 8 nurses on duty. Between 11 and 12, 9 nurses, and so on. We have 2 different types of nurses we can hire, and they can start at any hour of the day. Full-time nurses work for 8 hours, but one of them is a lunch break, and they cost £7.50 an hour. Part-time nurses just work for 4 hours, and they cost £8 an hour. So this ward would like to schedule their nurses, so we know how many nurses they're hiring and when they're going to start their shifts, so that the hourly constraints are satisfied, but also the total cost we are spending on wages is minimized. So how can we do this? Well, we can formulate this as a linear programming problem. So here I can just define some data structures. I've got a vector of variables. The variables are going to be how many full-time nurses are going to start at 9 o'clock, how many full-time nurses are going to start at 10 o'clock, up to how many part-time nurses are going to start at 3 o'clock. I have a cost vector, which is the daily wages of each of these types of nurses. I have an availability matrix, which shows for each column, which is the column is the variable and the rows are the hours of the day, whether that nurse is on duty or not. And I have a vector column of the constraints, the minimum number of nurses required. And when we put out the problem in this sort of structure, all we are doing is finding the vector x, such we minimize in cx, subject to bx greater or equal to a, and the vector x has got to be positive integers. Now, there's lots of linear algebra we can do to try and optimize this and work this out, but we don't need to do that because there's a library for that. It's called pulp. Pulp is how we can solve linear programs like this and optimization problems in Python. So with pulp, we define a problem as a minimization problem. We define all our variables, and I'm defining them here as integer variables, so I'm forcing them to be integer. I can then just add my objective function, which is that cx, to the problem, and add each constraint, which is the rows of that matrix, to the problem, and say everything's got to be positive. Then I can simply dot solve. Once I do that, I can read off the solution. The solution in this case being I should hire 1 full-time nurse starting at 10 o'clock, 2 full-time nurses starting at 11, 7 part-time nurses starting at 9, 4 part-time nurses at 1, and 1 part-time nurse starting at 3. So in quite small number of lines of code, we've solved a big scheduling problem for a hospital ward. Another area of mathematics operational researchers make use of is graph theory. And I'm going to use graph theory to optimally place a new hospital in my home of the Rhondda. So here I've highlighted some important towns. And I want to place my hospital in one of these towns so that the distance to all the other towns where the patients live is minimized. To help me along, I've used Google Maps' API to grab all the distances between the towns and create a distance matrix. And from here, 10 towns and a distance matrix, I can construct a graph or a network. This is a representation of that network where I've coloured the edges by the distance. So the more blue the edge, the longer the distance, and the more orange edge, the shorter the distance. Now, how can I choose a town which sort of minimises the distance to everywhere else? If we look at somewhere like Treherbert or Mardy, there's lots of blue edges coming out of them, so they must be far away from everywhere else. And if we look at somewhere like Llyn-y-Pir and Ystrad, there's lots of orange edges coming out, so they must be quite close to everywhere else. So I'm going to want to choose a town with lots of orange edges coming out of it. But can I do this in a more rigorous way rather than just looking at colours? Well, yeah, there's a library for that. It's called Network X. Network X is how we graphs and networks. So here I can create a network object D from my matrix of distances. I'm going to relabel the nodes as the town so it is easier to read off. And then once I've got our network object, I want to decide what's the most central node, what's the best place to put my hospital. But what do I mean by centrality? In graph theory, there's lots of different measures of centrality, and Network X has most of these built in. Network X also has really good documentation where you can read off what each of these centrality measures mean. And I'm not going to call myself an expert at graph theory, but I can look through the documentation and decide which one of them measures best describes what I think of centrality for this problem. I chose the betweenness centrality because that was a measure that took into consideration the shortest paths through the network, and I felt like if patients are going to travel to hospital, they're going to be taking shortest paths. So I felt like this was the most appropriate measure of centrality. I can rank all the nodes, so all the towns, by that centrality and return the maximum one. And here, the most central node is Ystrad, so I should build the new hospital in Ystrad. Now, in reality, in real life, there's more than just location constraints involved in here. But I'd like to just emphasise that this is a good approximation because the actual hospital in the Rhondda is in Llyn-y-Pir, which is just up the road, so that's a nice approximation. Dealing with randomness is something operational researchers do all the time. There's many ways we can do this, so we can look into probability theory and stuff like that. But when a system is very, very complex, we tend to resort to computer simulation. So let's take an example of this. We have a small A&E unit here that has 10 trolleys. We have 4 different types of patients arriving to this A&E. They'll queue up for a bed, spend some time in that bed in treatment, and then leave. So the 4 different types of patients, we have low priority, so with low severity, low priority yellow patients arriving randomly, but we know they come about 10 every hour. We have medium priority green patients with who arrive randomly around 5 an hour. We have medium priority pink patients who arrive randomly around about 2 an hour. And very high severe cases, high priority blue patients who arrive around about once every 2 hours. That's all random. They queue and for a trolley, and the higher priorities always are treated before the low priorities. From historical data, we know the patterns and distributions of how long they spend being treated in service. And the A&E manager would like to know, are we meeting targets? Are we providing the best care for our patients? How long are people waiting? So we can help them out. We can use some machine learning functions and scikit-learn to fit known continuous distributions to some of this historical data. And that might help us out if these are nice distributions and we can do some analysis on it. But in this case, the system is still too complicated, we're going to have to simulate it. But luckily, there's a library to do that. The library I'm using is called Q. It's something I've worked on quite a bit myself, personally. And it's designed specially for this scenario. So we have, first thing we've got to do is create a network object, and this describes the system. So this very carefully describes each different class of patient and each different their arrivals and how long they spend in service. We've got how many trolleys, and I've got their priorities. And we can add a lot of other behaviours in this, but this very accurately describes the system I just described. We can then create a simulation object out of that and run that simulation for a certain amount of time. And once we've run that simulation, we can just read off all the simulated waiting times. So I'm going to simulate it for 1 day. But what if that 1 day was a particularly busy day? Or what if it was just a fluke of random numbers that came out of this? So to be able to smooth out all this randomness, we can just run the simulation lots and lots of times and take averages. Okay? And in this case, we find that patients are on average waiting for a bed for about 0.12 hours, so about 7 minutes. Now this is incredibly useful information for that manager of the A&E to decide whether they need to invest in an extra trolley, which is going to cost a lot of money, whether they are meeting the targets set by the health board, and so on. Another way we can describe systems of behaviour, systems that have behaviour, is through system dynamics. In system dynamics, we can describe typically non-random systems, doesn't have to be, as stocks, flows, and influences. So in this case, we're going to model the spread of a disease around the room. To do this, we have a stock of people who are susceptible to be infected by that disease. We have a stock of people who have been infected by the disease, and a stock of people who have recovered after being infected by the disease. There are flows between these stocks controlled by taps. And these taps are influenced by other factors. For example, here, the tap between susceptible and infected, the stock of susceptible and the stock of infected people, is positively influenced by the infectious rate of the disease. It's also positively influenced by the number of susceptible people there are and the number of infected people there are. The flow from infected people to recovered people is controlled by a tap, and that tap is positively influenced by the recovery rate of that disease and also by how many infected people we have. So this is a nice way we can describe systems visually, but all this is in reality is a disguise for some differential equations where stocks are variables, taps are rates of change, and these influence arrows is multiplication. So we can write down our differential equations, and we'd like to describe the levels of these stocks over time. So we'd like to describe how the variables, Si and R, change over time. Now, do we really need a mathematics degree to be able to work out what's going on here? No. There's a library for that. SciPy has differential equation integrator functions called ODInt. And all we've done here is defined our differential equations as a Python function. That needs to be in a specific format, but it looks simple enough. We've defined some time period where we're going to integrate over, and we've chosen a starting vector. So my starting vector is 99 susceptible people in a room, 1 infected person in the room. How's that disease going to spread? We can plot the results of this, and we can read off the behaviour of the disease. So you see the susceptibles are the blue line. The number of susceptible people quickly drop. The number of infected people rises until there's not enough susceptible people left to infect anymore. Then the number of infected people starts dropping. And the number of recovered people rises over time. And we can see that once the number of infected people starts dropping, the rate at which the number of recovered people increase slows down. So we've described this system over time. Finally, I'm going to look at an area of mathematics which was popularised by Russell Crowe in A Beautiful Mind, called game theory. This is the analysis of interactions of decisions. So in this case, we have 2 hospitals. We have patients arriving to one hospital to get treated and patients arriving to another. But each hospital chooses a maximum capacity. Now, that's not really a maximum capacity, that's a decision, a management decision. So if a patient arrives to the first hospital and they are under capacity, then they're treated at that hospital. If they arrive to the first hospital and hospital 1 is under capacity, hospital 1 is over capacity, hospital 2 is under capacity, then they will be diverted to the other hospital, the under capacity hospital. But if a patient arrives to hospital 1 and both hospitals are over capacity, the hospital 1 must treat that patient, they haven't got anywhere else to send them. And similarly for patients arriving at hospital 2. These hospitals would like to choose a maximum capacity so that they are seeing as little patients as they can, because then they can give better care to their patients. What capacity should each hospital set? Now, we should be able to see that in this setup, each hospital's decision affects the other hospital's outcome. So their decisions are interacting. Let's simplify this a bit and say the only decisions they've got is setting a max capacity of 0, 40, 65 and infinity. Okay. In this case, we can write this as a 2-player game represented by this payoff matrix. The values of this matrix were obtained by using simulation, which I showed you earlier, but it can be obtained by other analytical measures. And we can read this off as follows. So if hospital 1 chooses a maximum capacity of infinity, and hospital 2 chooses a maximum capacity of 0, then we're here, and hospital 1 needs to treat 119 patients, and hospital 2 doesn't treat any patients. Now in this scenario, hospital 2 are doing the best they can. They've minimised the number of patients they're seeing, and they've got no reason to change strategy. Whereas hospital 1 are seeing loads of patients, and any other strategy they choose, they'll see less patients. So hospital 1 have got a reason to change strategy. And if they change their strategy, then we move up that column, and hospital 2 might have reason to change strategy. Then we move across a row, and so on, and they'll keep changing strategies. This is not ideal for the hospital managers, so they'd like to choose 2 strategies such that no hospital has reason to move, no hospital has reason to change. This is called the Nash equilibrium of the system, and how do we find that? Well, you guessed it, there's a library for that. It's called NashPy. Here we're just creating a game object, and we're inputting the 2 payoff matrices into that game. Then we're going to run an algorithm which will spit out all the Nash equilibria, and we're going to read off the result. In this case, hospital 1 should choose its second strategy, hospital 2 its second strategy. So both hospitals should choose a cut-off of 40 patients. Very briefly, I'm just going to put all these little toy examples I've shown you in context. This is my PhD. So I'm doing some analysis around a new community care measure that's being offered to older people in Geraint. And we're looking whether the introduction of this measure has had effect on demands of different parts of the healthcare system, and whether it's affecting the workforce requirements of these places. So with hospital managers, we mapped out this network of flows and using data analysis techniques and simulation in order to work out whether there's any changes in demand and map workforce on top of that. So thanks for listening. I hope you've had a little idea of what we do in OR and how Python's going to replace all our jobs. Thanks.
We have a little time for questions. Just as I mentioned before, just try and be brief, try and make sure they're really questions, and also speak up if you can, because the mics are.
Yeah.
Great talk. I have a technical question. The optimization library report.
Yeah.
Things involved in the environment.
I haven't tested it myself, but I know that it uses a lot of NumPy arrays, so you can get quite big there. And these, in reality, the problems we're looking at are a lot bigger than that. And so I'm guessing it does, because that's the kind of problems that the operations researchers deal with all the time. Larger problems with 30 dimensions and hundreds of arrays. That's what happens in practice. I'm guessing it does. I haven't tested myself.
Do you do any sort of distilling of your initial conditions into like the essential things? Because you could have a whole load of initial conditions that are related. So do you do anything like analytical component analysis or like number of beds is also related to the financial constraints of the hospital and things like that, and the financial constraints of the hospital due to the political climate or whatever.
So what tends to happen, the sort of process we go through is we look at what's happening right now. So right now we know there are 10 trolleys and we can't change that. But we can then talk with managers and go, well, what's a realistic scenario that might happen in the future? So the hospital managers know a lot more than us about their budget and like their future plans. So they'll come to us and say, well, we're thinking about splitting this into 2 wards of 6 beds. What would that look like if we've got the same number of patients going through? And that's an easy way to analyse our system. So I hope that answers your question.
Yeah,
the process we go through is working with the managers of this system. I know, talking about the lots of different influences about, when I was talking about system dynamics, I know a lot of work goes into sort of measuring sort of unquantifiable stuff. So we can have these influence arrows talking about, these influence arrows can be influenced by the political climate and they can be influenced by the general happiness of the population and stuff. And we can use system dynamics for stuff like that as well. Yep.
You talked about using these tools to do kind of linear problems and linearities. How do they scale to non-linear problems, obviously like SIR problems or like linear but in real life? So they interact with each other or not?
Yeah. So the SIR problem I showed there wasn't linear.
Okay.
That wasn't, yeah. And using the system dynamics, that's where non-linear stuff really comes into its own. For the optimization stuff, the technique I showed there doesn't really hold for non-linear systems, but there are other techniques we use. We use a lot of heuristic algorithms, which sort of very cleverly search the data space of all the different solutions and try and find optimal solutions there, and that is a big area of OR as well.
Thanks.
It's maybe a bit dumb, but is it actually in hospitals' best interest to take 0 patients?
No, this was a toy example, a very small toy example.
Okay.
So when I took an example of a paper that was written on this, and I simplified it a lot to be able to put it into a 1-minute slide. So, yeah.
Really quite a question. Have you got any advice on how you can find, how you can see the problems that these things might solve? So, every day in my work, for example, how would I notice if I've got something that could be solved by some of these techniques?
That's a good question. I think that's something that well, as operational researchers, we just sort of get used to seeing that sort of problem in things and get used to seeing that this problem, which might not seem related to anything, is actually just disguised for a timetabling problem and stuff like that. That does take practice.
Well, I think we're out of time, I'm afraid, but that's a very interesting